Now let's take another case, okay? So we still have these trees A, B, and C, and we still have averages 12, 13, and 11. But now let's say that our apples have the following content of, here we have 12.5, 13.5, 11.5, and then we have 13, 14, and 12 here. Then we have 11.5, 12.5, and 10.5, and then we have 11, 12. What's the difference? Well, if we calculate the average values, it will be still the same, 12, 13, and 11, right? So the difference between samples is the same. For example, the difference between 11, of course. The difference between B and C is 2, right? But now look, the variation within the sample is smaller. So the total variation of the sugar in each sample is smaller. Let's see if it's small enough to see the effect. We do the same. First of all, we subtract the average, right? So this ABC. So if you take 11, subtract the average, you remember the average is still 12. The average, the grand average is still 12, right? So if we took 11 and subtract 12, it will be minus 1, right? Then we have minus 0.5. Then you have 0. Then you have 0.5. And you have 1. Now we do the same for the second, so it will be, here we have 0, then we have 0.5, then we have 1, we have 1.5, and then we have 2. Then here we have minus 2, minus 1.5, minus 1, minus 0.5, and then 0. So this is our total variation of the sugar without the mean. So we just centered the values. So we are interested only how far they are from the mean. We don't interested in the mean. Now the average values will be the same. It will be 0, 1, and minus. Now the systematic part, because the average is the same, the systematic part will be the same, right? So if we don't have any random effects, we should have all zeros here. We should have all ones here. And then we should have all minus 1. Okay, so this is systematic part. Now the error part, we do it the same. So we need to take the total and subtract the systematic part, right? So minus 1, minus 0, it will be minus 1. And then it will be minus 0.5, 0, 0.5, and 1. And then if you repeat it for the others, you will get the same values. It's similar to what we had before, but the total variation will be smaller. You will see it in 1, minus 1, minus 0.5, 0, 0.5. Again, our values seems to be systematic just because I got this nice initial values for getting calculations easy. In reality, the residual variation, these values for the residual variation should be absolutely random. Now we do the same. We calculate the sum of squared values. The sum of squared values for the systematic part is the same. We didn't change anything. What will be sum of squared values here? Well, you remember that minus 1 squared is 1. And then minus 0.5 squared or 0.5 squared is 0.25. Then we have 6 ones, so it will be 6. Then we have 6, 0.25, which gives us 1.5. 1.5. And then we have zeros. So the total variation will be 7.5, right? So 7.5. It's a sum of squared values, 7.5. Okay. Now, the degrees of freedom. We remember the degrees of freedom, we started with 15. Then we use 1 to calculate average, it's 14. Then we use 2 degrees of freedom to make a group comparison, and then we have 12 is left. Now we can calculate the variance, just taking the ratio. So the variance for systematic part, is the same. It's 10 over 2, or it's 5. And the variance for the error part, it's 7.5 over 12. Which gives us 0.625. Then F value, the F value, it's a ratio between these two, systematic and the error. So it's 5 over 0.625, which gives us 8. And you can assume that this value seems to be quite extreme, right? So this is 8. Again, if we look at the distribution, okay, and then make this value, you remember if we have 2, let's say this is 2, right? When we got 2, this area on the right was about 18%, about 18%. Now we have 8, so it's like 3 times larger, 4 times. So what will be the area here for the 8? Well, we know that we can use R to calculate the area. It will be 1 minus CDF for F distribution. Now our value, the F value is 8, but degrees of freedom are the same. We still have 2 degrees of freedom for the first part, for the systematic part, and 12 degrees of freedom for the error part. Okay. The p-value we will get 0.0062. Okay, so it's 0.62%, less than 1% chance to get a sample like we have, or even more extreme, if there is no difference in average values of the population. And now we see that it's very extreme. So in this case, we see a difference. Because the sample is too extreme. There is still a small chance for making a wrong decision, right? It's exactly 0.62%, but it's very small. So the sample is too extreme from being taken from populations where there is no difference between sugar amount, okay? And then you can see that because the total variance, the variance inside each sample is getting smaller, now we can see this effect more clear. And now we can see that the sample is too extreme for not having this effect, right? So that's the intuition. That's how one-way ANOVA works.